So the last topic in kinematics that we are going to look at is known as relative velocity, sometimes also called Galilean relativity as opposed to Einsteinian relativity. And what this has to do with is your frame of reference. And maybe we should have done this towards the beginning of kinematics, but that's all right. Up until now, we've been saying, okay, there's an object moving at 30 meters per second, and it stops in this distance, blah, blah, blah. But we didn't say what the frame of reference was. Typically, when we say something like that, we're implying relative to Earth. But we can be more specific than that because it matters. And in fact, all speeds are measured relative to some frame of reference or some other object. And we can think about how those frames of reference change depending on the situation. So here's a pretty straightforward example of a one-dimensional situation. If you have a train traveling along, say at 60 miles per hour, and a person gets up and walks towards the front of the train, who knows, at 2 miles per hour, well, is this person moving 60 or 62 or 2, or what are they moving? It depends on your frame of reference. From inside the train, from their frame of reference, the person is moving at 2 miles per hour. From an observer outside the train, that person is moving 62 miles per hour. So you add the two velocities, the velocity of the train of 60 and the velocity of the person, obviously, to get the 62. If the person were walking toward the back of the train rather than adding those velocities, you would subtract them. So again, if they were moving 2 miles per hour, now in the other direction, relative to somebody on the ground, they would be moving 58, obviously. So that's nice and simple, right? So let's look at what goes on in two-dimensional situations. And before we jump to that, since we're going to have different vectors, some of you might not be familiar with this I, J, and K stuff. So this is just another way of saying in the X, Y, and Z directions. I don't know where this came from. But these are known as the unit vectors. So if you take the magnitude of your velocity times a vector of magnitude 1 in the direction of I hat, then that is in the X direction, and Y in the Z direction. Okay, so these are the types of problems that you're going to be seeing. If you've got a boat going across a river, you have different velocities relative to the water versus relative to the shore. And the typical strategy that your book uses, and many others, is to use this notation where the first subscript is the object that is moving, and the second subscript is what that velocity is measured relative to. So in this case, this velocity vector here is the velocity of the boat with respect to the water. So if this were a lake instead of a river, the boat would just travel in that direction. Okay, but you have the water moving, and so here, this velocity vector here is the velocity of the water with respect to the shore. That's usually how you measure the current in a river. And if you add those two vectors using vector addition, you can do that graphically or using components or trigonometry. Then you get this vector here, which is the sum of these guys, and that is going to give you the velocity of the boat relative to the shore. So the boat, even though it's angled like this, in this situation will be going straight across the river. So that's the motion of the boat relative to the shore. Another thing that you can use to check that you set up your vector addition correctly, if you use this subscript notation, the inner subscripts, you could say, are going to match, and then the outer subscripts here are going to match the sum over here. Now granted, if you swap the places here it won't work, but swap them until they do work, and if there's no way of getting them to work, then you have your vectors written wrong, and that's an indication that you might not get the right answer. Alright, a couple of examples. Back to this boat again, exact same situation, but now let's do some numbers. If we say the boat's speed is 1.85 meters per second, so that's this guy. If there were no current at all, the boat would just head that direction at 1.85, but we've got a current going this way at 1.2. And what is the angle that the boat must be heading if these are the two velocities? So in this case, we can just use some trigonometry. We've got a triangle here, and we have the opposite and the hypotenuse. So the trig function that relates those things is the sine function. And theta is what we want to find. So we can just say that sine of theta is the opposite, which was 1.2, over the hypotenuse, 1.85. You're going to have to take the arc sine of this, right? Theta equals arc sine of 1.2 over 1.85. And voila, you get a 40.4 degree angle relative to the line horizontal to the shore. Oh no, sorry, relative to the line perpendicular to the shore. Okay, so simple enough to get that angle, right? Now here we've got a boat, same river, so we've got these same two speeds, but instead of putting our boat at an angle relative to the shore, we're going to go straight across the river. So now the boat is heading this way, the current takes it that way, so its actual movement relative to the shore is going to take it off at an angle here. And we've got a couple things we're going to find. We want to know the velocity of the boat relative to the shore, so that's this guy here. And then we want to know how far, three things, how long it will take to cross the river and how far downstream we will end up. So let's start with part A. Again, we can just use trigonometry. We know these two sides of our triangle, so we can actually use the Pythagorean theorem to find the magnitude of this side of our triangle. So the velocity of the boat relative to the shore is going to be the square root of 1.85 squared plus 1.2 squared. And that is going to give us a magnitude of 2.21 meters per second. To find the angle there, since we know all sides of the triangle, we could use sine, cosine, or tangent, but it's always a good idea to use the initial values you were given in case you messed up in one of your calculated values. So if we're going to use the 1.85 and the 1.2, those are now the opposite and the adjacent sides. So that's not a theta. So we're going to use tangent, and I'm just going to kind of skip a step here because I think you guys are all experienced with this. So we'll do the arc tangent of opposite, that was the 1.2 over adjacent 1.85, and in this case we get a 33 degree angle here relative to going straight across the river. Alright, part B, we want to know how long is it going to take us to cross the river. Well, the fact that this current is pushing us to the left doesn't affect our motion across the river at all. So this is a really simple question. We just have the width of the river and we have the speed at which we're crossing the river. So we can just use delta x equals vt because that's our equation for constant velocity. Plug in 110, plug in the velocity across the river. Let me make sure I get the right one. This was 1.85, yeah. That was 1.20, so we're going to have 1.85, solve this guy for t, and you end up with 59.5 seconds. So that's the first part of part B. The second part says, how far downstream do we get swept? Well, that's not too tricky either because if if there were no current, we would just go straight across. If there is current, we get swept downstream. Or if we weren't going across the river at all, it's just how far do we go downstream in this much time. So again, we're going to use delta x equals vt, only this time delta x is what we're solving for, so this is down the river. We're going to have this velocity now, the 1.2, and that time, 59.5 seconds. I guess I should do meters per second if I'm going to do seconds there. So we're going to get an answer in meters. Comes out to be 71.4 meters that we are swept downstream by the current. Okay, one more example. Here we have two cars approaching an intersection, and they're both going the same speed, 40 kilometers per hour, or just over 11 meters per second. And we want to know what is the velocity of one car relative to the other. In this case, car 2. What does car 2 say about the velocity of car 1? So this is the perspective from Earth, so that's what this E subscript here is saying, or essentially from an observer on the sidewalk. They would say, okay, these guys are both coming here. But from his perspective, you could say that the sidewalk and all of Earth is rushing that way at the same speed that the person on the sidewalk would say the car was rushing this way. And at the same time, this car is rushing up, so the car is rushing up, and all of Earth is rushing that way, kind of like the current in the river. So this person, if they could imagine themselves at rest, would say this car is coming at me diagonally at some velocity here that we are going to calculate. Well, like the previous problem, we know these two sides of the triangle, and we're trying to find the hypotenuse, so we can use Pythagorean theorem. So this side is 11.1. This side is also 11.1, because we change our frame of reference doesn't change these speeds. It just changes which direction you say that things are going. So we can use Pythagorean theorem here, and we're going to have velocity of car 1 relative to car 2 is square root of 11.1 squared plus 11.1 squared, and that comes out to be 15.7 meters per second that the car is heading this way towards that car. All right, that's all. See you next time.